Okay, this is section 9.3. So section 9.3. And it's the t-test for means. Now, we just got done doing 9.2, which was for proportions. This is for means. So this is going to involve both a t-value instead of a z-score. You're going to use t-CDF instead of normal CDF. And you're going to use degrees of freedom, kind of like we did with confidence intervals way back in 8.2, I think it was, before we had break. So let me just give you an example of how this would work. Let's talk about offensive linemen in college football. And Sports Illustrated comes out and says that the average offensive lineman in the NCAA weighs 293 pounds. Now, someone's a fan of the Big 12, and they think, boy, in the Big 12 or the Big 10, either one of those two conferences, the Big 12 will go with, I think the offensive linemen are heavier. And so you randomly select 12 offensive linemen from various teams, and you come up with an average of 298 pounds with a standard deviation of 8.3 pounds. So the claim is 293 pounds in the NCAA, but in the Big 12, I'm coming up with 298 pounds on my average of 12 players. You can say I randomly picked one person off each team, or I picked just a random selection of 12 people from the Big 12. I want to know, is this 298 over here, change colors, is this 298 significant compared to 293? It's only a difference of 5 pounds. They say that's no big deal. But maybe it's significant, maybe it's not. This is why we do significance tests, because you don't really know until you do a test to see if that is a significant number. Sometimes very small numbers can be significant, sometimes they may not be. So, going back to my part here, the first thing we want to do before we do a t-test, this is what we do, is a one sample t-test. Is we have to check conditions and assumptions. And right now you guys should know what these are. By the way, in your calculator, this is just called a t-test. Under your stat test menu, it's just called t-test. But you should call it a one sample t-test. It just doesn't fit well into the calculator. So the check conditions and assumptions over here, and you guys probably know what they are. One, they should be random. And I told you these football players were randomly selected, so that's stated. Your number of players should be less than 10%. So we have 12 players here. Is that less than 10% of all offensive linemen in the Big 12? Well, if you have 12 teams in the Big 12 and each team has anywhere from 12 to 15 offensive linemen, there's probably anywhere from 144 to 160 so offensive linemen. So that would be checked. Or just say assume so if you don't know. Here's the crux, is that n should be greater than or equal to 30. Well, we only have a sample size of 12 up here. So 12 is not 30. So 12 is no. But I also told you, or if I haven't, I'm going to tell you now, that the distribution of these 12 players is nearly normal. And what you would have to do is actually put these in your calculator and graph them to see if they're nearly normal. They don't have to be normal, but just basically unimodal with no skewness. If there's a lot of skewness, then you can't do this test. So your condition assumptions are random, the 10% model. If it's greater than 30%, you're good to go. You can assume it's normal. If it's not greater than 30, then we have to say that the distribution looks nearly normal. And let's just assume for right now when I test it and I told you that they're randomly distributed. Okay. Now, for the next page, we have to get the formula. So the formula for this, first of all, is to get your significant score T, you're going to take X bar, the average of the sample, minus mu, the average for the league, divided by the standard deviation. So X bar divided by mu The standard deviation, if you remember from earlier in the year, is the standard deviation of the sample divided by the square root of n. So we're going to put s of x all over root n. So let's plug in our numbers in this case. We have the average of 298. We're going to go, the average nationally was 293. My standard deviation from up here was 8.3. And we have a sample size of 12. When you crank out that math, what you're going to get here is 2.087. And that would be your t-score. Now what that means is we want to know, with a normal distribution, because the conditions are met, that the average offensive lineman is 293, but in the Big 12 they are 298. Is that significant, being 298 or higher? This t-score here would be 2.087. And we know that is very significant. Okay, remember it's significant typically if it's under 5% p-value. So we'll go to the next page and we'll go ahead and set up then to get the p-value of that one. So we get a t-score, remember, of 2.087. What we have to do before we do anything else, I should have done this earlier actually, is we have to put our hypothesis down. Our hypothesis here is that mu is 293 pounds. That's what's claimed by Sports Illustrated. In the Big 12, though, I say it's not that. I did my own sampling, and I'm getting a number larger than 293. In fact, I'm getting 298. And I want to know if that's significant. So, t-value of 2.087, so remember, going back to this graph, we have this number here, and this is 2.087 out there. What's the probability of t being greater than 2.087? Shaded area here. And in this case, it's a sample of the mean, not a proportion. So our degrees of freedom, if you guys remember, is n minus 1. So 12 is my sample, minus 1, we use 11 degrees of freedom. When I put that in my calculator using the TCDF function, by the way, guys, on the AP exam, they're going to give you tables. You can use your calculator, but some of the stuff might be informative in tables. Look at the PowerPoint that I put in the lesson, and you can see how they use the tables. I still don't use my calculator. That's what I have. But what you're going to get here is when you put the TCDF in, your lower, I can type lower, is 2.087. Your upper, put in a big number, and then you use for mu 0, and for the standard deviation you put down 1. That then gives you a probability of 0.03. That is your p-value. Getting at the bottom of the screen here. So if my p-value is that, if I scroll up, I get a p-value of 0.03. This is a one-sided test. Remember, it's just an upper. We're looking at this part out here. So since the alpha level I said was 5%, this 0.03 is below 5%. So then you would say this. With the p-value of 0.03 and alpha of 5%, I reject the null. There is strong evidence indicating, and I'm going to squeeze this in, that weights are significantly higher in the Big 12 conference. Okay, so what we just performed here was a test of significance to get this. Now you can use the t-test on your calculator the same way, and when you do the t-test on your calculator, you go to t-test, you type in, go to stats, you'd have to type in this number here, the 293, you'd have to type in your X bar of 298, you have to type in your standard deviation, of, 8.3 pounds, in your sample size of 12, it'll give you the p-value of 0.03 as well. So that's using the technology. On the exam, I doubt they're going to give you one where you have to use your calculator. Probably going to do the information for you, just make you either reject or fail to reject a situation. Now, if this was a two-tailed test, and I just said, I think the Big 12, let me go down to here. I think the Big 12 is different than nationally. I don't say it's bigger or lower. I just say I think it's different. My alternative hypothesis would have been mu not equal to 293, in which case, when I got a p-value of 0.03 just a minute ago, if it's a two-tailed test, because I said it's not equal, it could be above or below, could be up here or down here, I would take my p-value of 0.03, multiply by 2, and get 0.06. Then with an alpha level of 5%, I would fail to reject, FTR, fail to reject the null because it's above 6%. This is a one-tailed test I did, though, because I knew it was 298. I suspect the Big 12 players are bigger. But the claim was I just think it's different. You'd have to do a two-tailed test, and you take your data and then multiply by your p-value by 2 to make your claim. Okay. Later on, I'm going to give you guys a video where we do what's called a matched paired testing. That's where you compare like before and after. So in other words, like kids' test scores in September and kids' test scores in May, you want to see how much they've changed. It's what's called a matched paired testing. That's the last part of chapter section 9.3. I'll do a separate video on that, though, because it's kind of different all by itself. Okay, hope this helps. Take care, everyone.